In this video, I'm going to go over the process of simulating data for a generalized linear model. Simulating data is something that Kerry does very effectively in his book, and it's something that we're going to be seeing a lot of in this workshop. To me, there's a great advantage in simulating data because it forces us to explicitly decide exactly what the process was that gave rise to the data. So in this particular instance, what we're going to have is a binary dependent variable. And we're going to say that y is equal to 1 if a person likes classical music. And we're going to say that y is equal to 0 if a particular person we sample does not like classical music. And so we're also going to assume that the probability of liking increases with age. And we're going to model a bunch of data based on some relationship between the age of the person and the probability of them liking. So what's a little bit challenging, you need to get your head around, is that there's two things that are happening here. First of all, we're going to create a model that predicts the probability of any randomly selected individual liking classical music. But that particular individual, when he responds to our poll, is going to respond with either a 1 or a 0. The response is going to be binary. Now, if this seems a bit strange, perhaps an example would serve. Think about what happens on the Weather Channel. What do you see? You see some probability of precipitation. Maybe there's a 30% probability of precipitation, but on any one day, it either rains or there is no rain. And that's a similar thing that's happening here. So we're going to model the probability of liking classical music as a function of age, but ultimately, when that person responds to our poll, we're going to get a 1 or a 0. So think about how we might create a model that says that the probability of liking classical music increases with age. Based on your previous courses, you might initially think, okay, we'll make a model that says PI, the probability that an individual likes classical music, is going to be some sort of a linear function. So this is the probability. Here's our linear function that says this is the intercept, this is the slope, and this is the age. Now, as it turns out, for reasons that will become apparent if you look at some of the supplementary material, we're not actually going to model the probability as a linear function of age. What we're going to model as a linear function of age is this thing here. The log of the probability divided by 1 minus the probability. And this is sometimes referred to as the log odds or the logit. That's going to be our model. So how are we going to simulate these data? Well, we're going to need some ages. So we're going to represent the age as x. We're going to have a bunch of ages here. How are we going to get those ages? We're going to get those from a uniform distribution that runs between 15 and 40. So we're going to assume that the people we sample have ages between 15 and 40. So we're going to have our ages. And then we're going to have our logit. And where's that going to come from? Well, the logit is going to come from, we're going to say that this logit is equal to this in general terms, and in particular terms, what we're going to say is that this, we can consider this to be some function of the age, and the particular function is going to be minus 0.43 plus 1.4 xi. So again, this would be the intercept. and this would be the slope, and this would be the age, and this would be fxi, which would be our logit. So we're going to have a whole bunch of values for this logit. And then if we know the value of the logit, we can determine the value of pi. How are we going to do that? Well, the formula is developed in your notes, but essentially if the logit is equal to some function of x, then what we can say is that p is going to be equal to f of x divided plus 1 plus e to the f at x. And that's developed in your notes. So now we've got a series of probabilities. And of course, being probabilities, they'll all go from 0 to 1. Now what we really need is our data. Remember what our data is. Our data is a series of ones and zeros. Where do we get our ones and zeros? Where do we get our values of y? Series of ones and zeros. What we're going to have for each individual is a value of p. And then these ones and zeros are going to come from our Bernoulli distribution. Here's our Bernoulli distribution. Remember, it's only got two outcomes, a 0 or 1. And this has a value of 1 minus p. And over here, we have a value of p. And so for each one of these individuals, once we know the value of p, we can obtain a random sample from the Bernoulli, and that's going to give us our value of y. So there's something that's really happening here that is probably a shift of what you've been thinking about in your previous courses. So thinking in your previous courses, let's say you were weighing some pigs and you had some linear model that said the weight of the pig was equal to alpha plus b xi. And the way you might model that is you'd say, okay, you're going to create some linear function that gives you an estimated value of weight. And then what you do to it to get the actual values, the observed values, is you'd add a little bit of noise in the form of an error function. And typically, this error component would be assumed to arise from a normal distribution with some sort of a mean 0 and a standard deviation sigma. That's not what we're going to do here. What we're going to do here is we're going to have our values of p that are going to go from 0 to 1. So we're going to have a whole bunch of values of p here. And then what we're going to do is we're going to assume this Bernoulli distribution, and then we're going to randomly take a value from that Bernoulli distribution, and that's going to give us our y. So quite a different process from what you generally experienced in the past to what we're going to do when we simulate data for a generalized linear model.